So we'll first have Professor Roger Ulrich of UC Los Angeles, then Jørgen Christensen-Dalsgaard of University of Aarhus, and Conny Aerts from KU Leuven. But we'll start with Roger Ulrich.
Okay, thank you. Yes, well, this is a real surprise to me. The work for which I got this award was done back in 1970, and so it's a long time ago. At the time of 1985, I took up the responsibility of managing observations from the Mount Wilson Observatory, which is this beautiful picture. And at that point, I essentially stopped doing helioseismology and became a magnetic field measurer, a Doppler shift measurer. And so I've done a lot of rotation, but I'm really quite pleased to have this award and continue the work of that others have been doing in the meantime. So the start of helioseismology really began with Bob Layton, who is shown here. This is Bob Layton, and he was a very clever experimentalist, and he devised a way of imaging the Doppler shifts of the gas on the solar surface. So we would make a map of the solar surface, and he found that, in fact, the solar surface is going up and down with a period of about 5 minutes, and that became identified as the 5-minute oscillations, which essentially form the basis of helioseismology. But from my perspective, one of the key events was Ed Fraser, who was a fellow graduate student. I was at Louis Hagnier's group doing stellar evolution calculations at UC Berkeley, and he was sent off by Louis Hagnier to study this obnoxious phenomenon that we had to deal with called convection, and nobody really understands it even now with the kind of precision that would be required. But he sent Ed Fraser off to make a series of Doppler maps of the solar surface, and this is a picture of Ed in observing the image down on the area. Whoops! Oh dear. Okay, so let me see okay, there we are. So this little circle down here, part circle, is the solar image, and he was measuring Doppler shifts on the solar image. And so that information that came from his studies was essentially the trigger that got me started wondering about how the solar oscillations actually work. Let's see. This is the image that he created, not Ed Fraser. This is from Bob Layton's group. They had a really clever Doppler subtraction technique which brought out the solar oscillation pattern as well as what we now know to be the granulation. So the Doppler shift velocities at the disk center are essentially entirely the solar 5-minute oscillations, and as you move out towards the edge, you start to pick up a contribution from what we call supergranulation, very large convective cells that are tunneling their way through the solar surface. And one of the things that he mentioned in this, in the references at the back, is this private communication from Bob Howard. Got the right thing here. So Bob Howard has a system at Mount Wilson as well. This was all done at the Mount Wilson Observatory, which is where that snowy picture was from the beginning. And Bob has this this lever arm here as a big meter stick, and as he was doing his setups and other things to measure magnetic fields, which was the primary goal of this system, he noticed that this adjacent meter stick was going up and down, and he said, oh, it's about a period of 5 minutes. I don't know what's going on. But he essentially said nothing about it. And then Bob Layton came along and discovered that it's actually this 5-minute oscillation process that is what we use to do what we now call helioseismology. Anyhow, that was sort of the origin of the approach that I took. The modern image here, this is a more recent image like the one that Bob Layton had created, but you can see the pattern of the oscillations going to a lower amplitude where you don't have the combined 5-minute oscillations and the supergranulation both influencing the Doppler shift of the solar surface. The gradient from one side to the other is due to rotation. And this little jet here is probably an emission from a sunspot phenomenon going on. So the thing that I felt was important was to try and understand how these 5-minute oscillations were actually propagating through the solar envelope, and I thought that this was a potential source of information about the solar interior, because these were evidently waves, and it seemed to me that they were described as acoustic oscillations. And so what I did was to try and find a way of looking in more detail at this diagram, which we call the Diagnostic Diagram, which is a combination of measuring the wavelength of the oscillations and their period or frequency going up and down. So we have frequency going in this direction and wave number going in this direction. And what I wanted to see was how the material actually went through the outer envelope. Ed Fraser's observations had indicated that, in fact, the initial idea of the generation of the waves, which was that they're basically noise created like a jet engine from the convective envelope, up and down motions of the convective cells, that mechanism is called the light-hill mechanism, and the early papers on understanding what was going on were emphasizing the light-hill mechanism and talking about the origin. I was interested in finding out what we could learn about the solar interior, because these waves are traveling through the gas and are influenced by the local sound speed. So this is a modern diagram generated by Douglas Goff. It's very nice. I've done similar diagrams, but they're not as nice as Douglas's. And what is going on is the waves, which have a relatively short horizontal wavelength, don't go terribly deep. As the wavelength gets longer, the waves bounce around over greater distances and penetrate to a depth which is deeper. So each wavelength of the oscillations provides us with information about a different set of matter, and by using mathematical inverse theory to subtract the effect which is common to all of them near the surface from the effect which has both the surface and the interior, and the deepest ones, which are essentially global oscillations, bounce around like this. So we have a mix of seismic information that we can take out by combining the data from the different wavelengths of light. So this is my contribution to the subject. I did also spend some effort in trying to understand the generation of the acoustic waves. Their amplitude is modest, it's not huge, but according to the theory that I developed at that time, they should be overstable, which means that they're self-generating. And that analysis seems like it might not be totally wrong. It's certainly not totally right. And the problem with it is then how do you determine the amplitudes that are actually present? They should be probably larger than they are. So there's some complicated thing going on. The other idea is that they're generated by the effect of 1,000 feathers hitting a gong, and so we wind up with relatively weak oscillations. At any rate, the thing that I determined, which was novel, and I think it ultimately the important generation of helioseismology as a field, was to find that there are these resonant lines. This is the first overtone. It's called the F mode. I know now. I didn't know then. I called it the P0 line, but that's okay. And then the next overtone is a little bit higher. And third, I only did 4 because I had limited resources, and I had a particular convective envelope that I was analyzing. And so what you need to do to get this is you have to resolve the solar image into different wavelengths along this axis, and then at each wavelength you measure the power spectrum going up, and then the locations of the peaks should be along these lines, which I have 1, 2, 3, and 4. And the power that people had seen at that time are indicated in this particular diagram. The Ed Fraser observations are pretty much compatible with the F mode and the P1 mode, which I label as 1 and 2 here. And then the higher overtones, 3 and 4, kind of get munched together in a thing that I have a big circle for, the one-dimensional scans, where they didn't actually resolve the wave number. They had just one dimension. This quantity down here is labeled as KH. It's the horizontal wave number. So if you have a wave which is going from left to right, you get a KX. And if you have a wave that's going from bottom to top, you have a KY. And case of H is the square root of the sum of the squares of those two wave numbers. So that was the thing which was lacking in the early observations, was that the people were doing just one-dimensional scans. And so the actual waves, that the frequencies that they got were all mixed up, and you couldn't see the peaks that are predicted to be there. So this is the first case where someone actually got good data that was able to test this idea of the resonant lines. It was a kind of saga. I put out my prediction for where the lines should be, and I waited a couple of years, and basically nobody was coming forward to test this idea, and so I recruited graduate student Ed Rhodes to do these measurements. And at the time there wasn't really any good measuring system available. We tried several places, and eventually at Sac Peak, George Simon, who'd been on the initial discovery of the 5-minute oscillations, was a resident astronomer at Sac Peak, and he helped Ed get things together. In the meantime, just as Ed was finishing up his analysis, the analysis is actually not that trivial to do, and he was getting ready to publish his results. Franz Stoibner in Europe came out with his announcement of this diagram, which we have here. So this is the first effort at verifying my prediction, and you do see that, in fact, the power falls roughly along this fingery pattern. My curves that are shown on here are a little bit too high. If you go on and look at modern data, I've transferred my frequencies over from the early paper and put them on this diagram. You see that, in fact, my lines were too high in frequency, and that's because my convective envelope model was done with what was a popular parameter at that time. This L here is the spherical harmonic number. It's essentially the wavelength divided by the solar, it's the wave number divided by the inverse of the solar radius, divided by the solar radius. The L that I talked about for doing convection models is what's called the mixing length. And so there's a traditional notation collision that these are essentially the horizontal wave numbers down here in the bottom. So my convective envelope was too shallow, had too high a temperature, and so the frequencies that I came up with at a particular L value were too high. This is one of the publications that I did early on to test my idea that we could, in fact, learn something about the structure of the solar envelope. The parameter that I describe it by is here the mass of the solar envelope divided by the solar mass. So this higher mode line of the two is definitely too high. And this particular ratio of masses was something that was actually my main source of employment most of these early years, which was working on the solar neutrino problem, wherein there are a factor of about 3 too few solar neutrinos produced by the theoretical solar models. And the envelope model that you need if the sun were swept out so it has very few heavy elements in its interior, the opacity of the solar material becomes less because these heavy elements provide most of the opacity. So this was a theoretical model that could have been a true representation of the sun. And if you had a model like that, then in fact the neutrino flux problem doesn't totally go away, but it becomes much less. But this diagram clearly shows that that idea doesn't really work. It's sort of contradicted by the helioseismic measurements. This is a more concise illustration of that result, where you can see the different modes along the bottom with a series of frequency excuse me, different frequencies that are generated by the different L over H. This L here is the correct symbol that we use for the mixing length, and this is the log of the mass of the convective envelope that is associated with these values of L over H. And you can see here that the helioseismic evidence clearly points towards a fairly high value of L over H. So that was one of the early results that Ed Rhodes and George Simon and I came up with in this paper in the Astrophysical Journal. This is a plot on the K omega diagram, which call it the diagnostic diagram, with again the case of H on the bottom and the frequency and angular frequency units on the top, and the various potential models that are there. I point out the one that fits when you do a solar model a total solar model, you don't have a choice of what the L over H is. The model tells you that. And you can see that, in fact, the total solar model is not too far off from where it needs to be. So this got me engaged with the community. My feeling was that we needed to improve on those diagnostic diagram observations. And so in the early 80s, we generated a meeting in Boulder, Colorado with a bunch of people who were doing solar physics there. We also engaged with the people over in Europe who had a project called DISCO, which was a spinning spacecraft concept that was designed to measure these oscillations from space. The advantage of space is that you get to observe it essentially 100% time, so you don't have the effects of the sun going up and the sun going down, and you get a much cleaner power spectra out of that. And so this early meeting in Boulder, where I actually showed something that was kind of an example of where the overlapping modes would cause some problems with individual peak observations, and it was kind of an ugly picture that I put together. I don't have it, but it had crosses and all the vertical lines for each mode that would be impacted, so it was kind of like a cemetery, and that was probably a bad idea. But anyhow, the meeting was successful, and Yuri Tumri, Ed Rhodes, Jack Harvey, and I organized a snowmass meeting in 1983, which was attended by the NASA manager who was impressed by the outcome, and so he went back and started lobbying the NASA headquarters people that we should really do something. And so there was what we call a trilateral meeting with ESA, NASA, and the Japanese Space Agency, ISAS, where we talked about solar terrestrial science, and there are many things besides helioseismology that could be done on a spacecraft. And eventually there was an International Solar Terrestrial Physics Program, ISTP, which defined both the SOHO spacecraft and a group of other spacecraft to measure the solar wind out near the Earth. So these two spacecraft were part of this ISTP program. And the contribution that I made was that we defined the things that needed to be done on this SOHO spacecraft, which were then implemented. And so the NASA came out with an announcement of opportunity, and we competed to build the instrument, and we lost the competition. So Ed Rhodes and I and people at JPL had an idea that would have become SOHO, but been the instrument on SOHO, but the people at Stanford with Phil Scherer and Todd Hoeksema and others succeeded where we didn't. But that's okay. I wouldn't have done the Mount Wilson program if I'd been more involved with SOHO. And so this is kind of the most recent thing that I was involved with. The results from SOHO provided really good frequencies, and we use what's called inverse theory to calculate the structure of the sun, and this diagram over here shows how well our models are doing relative to the solar interior. And there's clearly some issues with what we're doing at the boundary between the convective envelope and the surface. The surface layers are kind of crummy in this diagram, but they're not too bad. There's more work that needs to be done up there at this time. And so there was a bunch of models that were were done, more than these two that are shown on the diagram on the right. And so we were able to do some error analysis for the various experiments which were going on. So the predictions for the chlorine experiment that John Bacall, who was my mentor at this time, was doing with Ray Davis, had this tank of perchloroethylene that was being measured for the impact of solar neutrinos, and we came up with this. The theoretical variance is about 1 in these solar neutrino units, whereas the actual detections are about 2.5 with an error which is pretty small. So the discrepancy between the theory and observation is significant statistically, and that was one of the ways that we kind of got around the problem with understanding what was wrong with the chlorine experiment. The experimentalists would point at the theoreticians making models of the sun, and people making models with the sun would point at the people calculating the neutrino fluxes or calculating the neutrino rates. So there was sort of a trilateral shooting match going on, and this one basically said, no, it's not the models which are the problem. The models are pretty well confirmed with the helioseismology, where the errors are not that big. And so we got the neutrino physics people basically to find the oscillations of solar neutrinos. So this is kind of where I ended my time as being a helioseismologist. I've gone on to do the Doppler shift material. This is a recent publication that I've hoped would be accepted by now, but they claimed they'd give me a decision in 5 days, and I submitted it 7 days ago, and they haven't gotten back to me. So it's still not, it's not accepted yet, but I think it will be. And so I found that there are these times at solar minimum where the polar regions are coming towards us. This is the line of sight velocity along the solar surface. This is the rotation rate variation. These things are called torsional oscillations, and they've been known for quite a while. So this is not known. This is the new thing, that there's a reversal of the meridional circulation, which describes the flow of the material from the equator towards the pole. So I'll stop with that little tidbit, which hopefully will get out there at some point.